Hi, my name is Joanne Truong, and I'm a first-year robotics PhD student at Georgia Tech. And first off, I just want to thank the organizers of this challenge for inviting me to speak at this workshop, and also I want to thank them for all the effort that they put into running our experiments, both in simulation and on the real robot. And in my presentation, I'll go over my approach and some things that I learned while participating in this challenge. So to begin, we approached this problem from the perspective of sim-to-sim transfer. We trained all of our models in Habitat, and we were trying to transfer to the Gibson simulator. We used Habitat to train our models because we wanted to leverage the large-scale reinforcement learning infrastructure that was already in place. And specifically, we used DDPPO, which is a decentralized distributed proximal policy optimization method. So the authors of DDPPO show that large-scale training allows us to train point goal navigator agents with an SPL of around 8.6 within 100 million frames. And they also show that when the agent is trained for longer, it actually continues to learn and can learn to navigate with near perfect SPL when scaled. In the end, their agent was trained for 2.5 billion frames of experience. Now moving forward onto the agent and model architecture, again, we follow the architecture described by DDPPO, and here the agent gets its input, an image, and also the goal vector. The image can be either RGB or depth. So this image is then passed through a resonant 50 visual encoder, and the output of this visual encoder, along with the previous action and the target relative to the current state, is fed into a two-layer LSTM. This LSTM outputs the next action and an estimate for the value function. So next I'll go over some experiments that we conducted using agents trained with DDPPO in the Habitat simulator. Here we tested 9 different models in identical experiments in simulation and reality. And the goal of these experiments was to measure the correlation between models tested in simulation versus reality. So we evaluated our models using a metric we call Sim versus Real Correlation Coefficient, or SRCC, which quantifies the degree of predictivity between performance in simulation and in reality. So here the x-axis represents our success in simulator, the y represents the success in the real world, and these are 9 different learning-based navigation methods that we tested out. SRCC value is close to 1 indicate high linear correlation, which suggests that our performance in simulation would correlate highly with performance in reality. However, using the simulator settings from the 2019 Habitat Challenge, we find that there is a low SRCC correlation, which suggests that the results and winners may not be the same if the challenge were run in the real world. So we discovered that the key factor that leads to this low Sim2Real predictivity is due to a sliding behavior in Habitat simulator. So when Habitat collides with the final location for a forward action, it first computes the location the agent would end up if this step were collision-free. Then it searches for the next navigable location closest to the collision-free point, and finally the agent is moved to this found location, effectively sliding it around obstacles if necessary. And since SPL is calculated using the straight line distance between the 2 points, this cheating by sliding behavior enables the agent to receive a high SPL by exploiting the simulator's imperfections. We were able to tune the simulation parameters and optimize for SRCC, and now we have simulation parameters that will have highly linear correlation between performance in simulation and performance in reality. And so to summarize, the training configuration from our best model from the previous experiments were trained with sliding off, with actuation noise characterized by PyRobot, and it took as input 256 by 256 square images. This was trained for 500 million steps on 64 GPUs. And at test time on the Gibson simulator, we would upscale the image and center crop so that the image resolution would align with our model. We also use a fast depth model, which is a monocular depth estimator, to predict depth using RGB images. And this is to combat the noisy depth input that would be present on a real robot. And this is the configuration for the model that was tested in the end for the real world phase of the Gibson challenge. So here we show our model navigating in a real world setting. So although this model worked for us in reality, we did face some challenges when transferring from Habitat to Gibson. Specifically, there were some differences in the simulator and with the action spaces that we had to deal with. So when working with the two simulators, I noticed that there was a height difference despite having set the agents at identical heights. And upon further investigation, we found that this was due to a voxelization error threshold that was set when computing nav meshes in Habitat. We were able to easily fix this error by recomputing the nav mesh with smaller error thresholds. And so now you can see that the images are more closely aligned between Habitat and Gibson. The next challenge that we faced was transferring between the two different action spaces. So Habitat works in a discrete action space where agents can choose between three actions, either moving forward by 0.25 meters or turning left or turning right by 30 degrees. On the other hand, Gibson uses a continuous action space, which consists of controlling the robot's linear and angular velocity. So our first attempt at a discrete to continuous control was to use a bang-bang control. This means we would simply command full linear velocity and zero angular velocity for forward actions, and the opposite for turning actions. However, we noticed that this led to certain actions being ignored, since it took a couple time steps to either ramp up or ramp down to the velocity needed to move forward or turn by our desired amount. So here you can see an example of this. Our agent is commanded to turn right for a couple of frames, and when it decides that it wants to move forward, because it has ramped up all this angular velocity, it needs a couple frames to ramp down. So it continues to actually move right for a couple of frames before it can actually execute the desired action. And to combat this, we implemented a proportional controller to interface with our high-level policy to ensure that each forward action would move our agent by 0.25 meters, and every turn would move our agent by 30 degrees. So here's a sped-up example of this. And now that our agent has a better control over its actions, it's able to make its way through a narrow doorway. So we also trained some additional models with the fixes that I mentioned before, along with some additional changes to match the configuration parameters from the challenge, which include switching our image resolution to 160 by 90, fixing our sensor height and sensor orientation. And we also tried using a proximity sensor for training to add a reward penalty whenever the agent got too close to an obstacle to discourage collisions. Unfortunately, we didn't have time to submit these results to the challenge, but we hope to continue to improve upon our model and hope to develop a navigation agent that is generalizable and robust to noise in the real world. With that, thank you.